Okay, welcome back. Mr. Nolde here. So, sports fans, calculates specifically, we're talking about related rates problems. This is probably something that you're doing right now in class if you're taking the calculus over a whole year, especially in high school. So, related rates problems can be tricky, and they usually come in at the end of learning how to do implicit differentiation. So, here's where the implicit differentiation comes in. So we have a situation where we have a ladder, let's say a 25-foot ladder, and it's leaning up against a building. So there's the building, there's the ground, presumably at right angles to one another. Put a little right angle in there. So this ladder is 25 feet long, right? So that's my ladder. So I'm looking at a right triangle here, right? So my 25-foot ladder is leaning up against the ground. So suppose we have a trickster, right? Somebody who's going to come along and slowly pull this ladder away from the wall. And suppose they're going to pull it away at a rate of, 2 feet per second, say. So I'm going to write down dx dt because that's the change in the x direction per second. So that's going to be equal to a 2. So dx dt is 2. So here's the thing. We want to know, this problem asks, how fast is this sliding down? In other words, what's dy dt? At the instant that the ladder is, the base of the ladder is 7 feet from the wall. So that's what makes this a calculus problem, because it's a rate of instantaneous change. The instant this ladder is 7 feet away, how fast is this dropping? So one of the things we have to figure out, and we can use a little Pythagorean theorem here, or if you have your triples memorized, this is a 7, 24, 25 triangle. So 7, 24, 25. So at the instant the ladder is 7 feet from the house, the base of the ladder, the top of the ladder is 24 feet from the ground. So let's write an equation here. So here's my equation. We're going to have an x squared plus y squared equals 25 squared. So 25 squared, that's 625, right? A common mistake is students will put the numbers in here first, but we don't want to do that. We want to start with our equation. And why are we using 25? Does the length of the ladder change? The ladder is always going to be 25 feet long. So that's why we use 25 squared here. So I want to find out dy dt, right? This is what I'm looking for. And I know that dx dt is 2, or 2 feet per second, but we'll just stick with the 2, dy dt. So what we need to do is, it's a rate of change. So that tells us differentiate. So I'm going to differentiate this with respect to t because it's a time-based problem. So I'm going to have 2x. If I differentiate x squared, I have 2x, and then it's dx dt. All right, next I have 2y dy dt. And the derivative of a constant, the derivative of 625, well, that's going to be 0. So now I'm going to make my substitutions. Don't make your substitutions first. Make them after you've differentiated, because you're looking for a rate of change. So 2x. So the instant that we are 7 feet, so I'm going to write 2 times 7, that the base of the ladder is 7 feet from this wall, and it's being pulled away at a rate of 2 feet per second. So substitution's okay on this one. Plus 2, all right, the instant the ladder is 7 feet from the base, the top of the ladder is 24 feet from the ground. So we need to put the 24 in for the y. And dy dt, that's what we're looking for here. So I'm just going to write dy dt is equal to 0. Then we could go about simplifying here. Let's see, I have 4 times 7 times 2. That's what, 28 plus 48, 2 times 24, dy by dt. And that's equal to 0. So one of the things I want to do is solve this. So I'm going to subtract 28 on each side. And then we have this. 48 dy dt equals negative 28. And the last step is we're going to divide both sides by 48. So I have dy dt, my d's are getting shorter, negative 28 divided by 48. And you can reduce that if you want to, or you can just type it into a calculator. Let's see, that reduces to negative 7/12, which would be about 0.583 repeating, right? And that's in feet per second, right? So when this ladder is being pulled out at a rate of 2 feet per second, the top of the ladder at that instant, the instantaneous rate of change is negative, means it's coming down, but 0.583 feet per second while that's coming down. So this is the way that we set up one of these problems. Again, one of the most common problems I have seen is that students want to start substituting right away into this. But you have to write the equation out so that you can differentiate, because we see that it's a rate of change problem. So this is a related rate problem. Appreciate it. Thanks for watching. Stay tuned. We'll do another one the next time.